Okay guys, let's get going. This is going to be the first video on determining the rate orders of our various reactants that we're going to be using when we're talking about kinetics. Now, as a quick recap, you're probably familiar with this equation, the rate law equation. So I'm just going to write this, that the rate law, we write it like this, right? The rate of the reaction is equal to the rate constant, which we write as K, is equal to the concentration of one of our reactants, I'll call that A in this case, raised to some order that in this case is like an exponent, that's going to be M. Now, in the case of, let's take a look at our problem. So in the case of our problem, we're given a set of data where the experimentalist changed the concentrations of the various reactants. In this case, the mercury chloride and the oxalate ion here that we see. And if you held one constant and changed the concentration, the initial concentration of the other, and recorded the rate of the reaction and how it proceeded, you would be able to determine how changing the concentration of one alters the rate. And that's rather useful because using these rate laws, we can then become very efficient in our processes. So if, for example, if you're working in industry and you need to make your reactant, which is the product you're selling to consumers more efficiently, you should know the optimal concentration of your reactants and what concentration should you have of both in this vat that you're brewing them in. So let's get started and let's figure out how this works. So as a recap, remember this, what we're doing right now is called the method of initial rates. And that's just it's called that because all of these concentrations that you see here in molarity are initial rates of these different reactants. So as a quick recap, the rate law is equal to the rate constant. And in this particular case, we have this mercury chloride, and it's going to be raised to some order M that we don't know yet. And we have this chromate right here, or rather not chromate, sorry, oxalate, O4, 2 minus, raised to some N order. Now, it is very imperative to remember that the coefficients that you see in the balanced equation up here do not represent the orders M and M. They are not the same. We will get down later in this video series that if you have an elementary equation, then those coefficients become the orders, but we're not there quite yet. So let's just get started with the basics. How do I determine what M and N are? And as a basic rule, we're going to look at the different concentrations that they gave us in the beginning. And let's look at that. So in experiment 1 and 2, they kept the concentration for mercury the same at 0.105 molar, but they altered the concentration of the oxalate by 2. It was actually increased by a factor of 2 because 15 times 2 is 30, so they increased the concentration by a factor of 2. Now, what happened to the rate in that case? Well, let's take a look. As a general rule, I say divide the larger rate by the smaller rate. So when we do that, we get something that looks kind of like this. 7.1 is 10 to the negative 5 over 1.8 times 10 to the negative 5. Notice the 0.5s the exponents will cancel, and you're left with just 7.1 over 1.8, which if you do that math, 7.1 you get 3.94, which is, for all intents and purposes, is fairly good for us. So we'll say that goes to 4. We'll say, well, that rounds up to 4. It's 4 times the rate. So let's take a look what that means. So if we kept our concentration of mercury the same, but doubled our concentration of the oxalate, and our rate of the reaction increased by a factor of 4, how do I interpret that? What should my order be for, or what should the N be in this case for oxalate? So in order to determine that, here's a general cheat sheet. In the next video, I'm going to go over a more quantitative way to determine these numbers. So in this video, let's go over a more quick way to do it if it's an easy to see problem. So what I like to do is implement this equation that a couple people use that I know of. So the way we do this is we look at the change in the concentration in brackets. In this case, our exponent, our order of this was n. And what was the overall change in the rate? So let's just plug in our numbers. So our change in our concentration was a factor of 2. We doubled our concentration. What happened to our rate? It went up by a factor of 4. So 2 to what number, what exponent gives me 4? Well, n must be equal to 2, because 2 squared is equal to 4. So I have my order for my oxalate ion. So the order is going to be 2. Okay, so knowing that knowledge now, we can continue with the other stuff now. So now let's take a look at our mercury chloride. So in a particular equation from 3 to 2, it looks like this doubled by a factor of 2x up here. Unfortunately, we kept our concentration the same for our oxalate, so that's the same. So notice that I'm always going from the low to the high, because you can go from high to low, but I just feel like it's from an intuition perspective, it makes more sense to go from low to high. So let's take a look what happened to our rate. Well, if we take a look right here, we see that it went from 3.5 to 7.1. So let's take a look. So because our oxalate was held the same, we can only look now at our mercury to see how that affected our rate. So let's take a look. Let's do our math again. Was it 0.105? 0.105 or 0.052. That's just a factor of 2, like I said. Now let's look at our rate. So 7.1 times 10 to the negative 5 over 3.5 times 10 to the negative 5. Well, like I said before, the times 10 to the negative 5 will cancel. So all I'm left with is 7.1 divided by 3.5, and the number I get there is 2.02, which for all intents and purposes is the number 2. So let's implement our little cheat equation before. The change in concentration, what was it? It was a factor of 2. So it was 2 to the m power is equal to my change in my rate, which was 2. So what number does 2 need to be raised to give me 2? Well, m must have the order of 1 in this case. So I know my orders here. So now I can actually solve for my overall rate law. So let's do that really quick. So let me put this in different color. Well, my rate law is going to have some arbitrary rate constant like that, so K. And it would be that HgCl2 to the m power, which happens to be 1 in this case. And then I have my, let's see, the C2O4, right? 2 minus. Raised to the second power. And this right here that we see here is what we call the rate law. So if you ever have an equation, or rather a problem asking you for the rate law, this is what they're referring to. The whole expression that we see here that tells us the exponents that the different reactants are raised to. So this is what we call a rate law. I hope this was helpful. As a quick recap, take a look at the different experimental data they give you. Find when one concentration is held constant and the other is altered by some factor. Analyze what the rate change was for your, from reaction to reaction. And then we can implement our little equation here. The change in concentration of N is equal to the change in the rate, as we see here. So once you do that, you can get your rate of your orders of your reactants fairly quickly. But I think in our next video, what we're going to do is, what if the numbers that we see in the change in the rate aren't as clear cut as, for example, 3.94. That's clearly 4. But what if I had something kind of in the middle? What exponent would I have to raise it to give me that answer? In the next video, we're going to go over a quantitative approach to solving for our rate orders. In the meantime, I hope this was a helpful video. We'll do one more on determining rate orders, and we'll continue with our kinetics videos as we go on. So, hope you have a good one. Thank you for watching.